In this video, I'm going to discuss spherical polar coordinates. This may be familiar from calculus or it may not, but it's good to review. The main reason we're going to need to do spherical polar coordinates is because if you have a spherical system, it turns out that x, y, and z are not related in any simple way so that they can be decoupled. So what we need to do is find a set of coordinates for a sphere in which we have three variables which can be more or less varied without changing too much the others. Okay, and so the choice we make is spherical polar coordinates. Okay, so the coordinates we're going to choose are related to, if you think about the Earth as an example, there's a great circle which is called the equator on the Earth, and so that's going to be the xy plane. The axis of the Earth is going to be the z-axis. Okay, now any vector, any position on the planet can be specified by the distance from the core of the Earth, which we more or less assumes just whatever the radius of the Earth is. So when you get directions, that doesn't tell you how far from the center of the Earth you are. However, it does give you two angles, latitude and longitude. Now, on planet Earth, the North Pole is 90 degrees north, equator 0, and then you have 90 degrees south. So the range of angles with respect to the vertical is 180 degrees. In spherical polar coordinates, it's defined a little bit differently. If the arrow is pointing straight up, that is 0 degrees. So this theta angle goes from 0 to pi. Okay, so you do need to know these integration ranges. In order to do integrals. Okay, so the phi angle does a circle, so that's 2 pi. And of course, if we have a hydrogen atom, the distance from the nucleus can be 0 or all the way out to infinity. So r goes from 0 to infinity. Okay, you can't have a negative distance. All right, and so if we define our center of our spherical system as the origin, then the distance is going to be r. It's going to be related to x squared plus y squared plus z squared. Whereas if it didn't have an origin, you'd have the distance formula where you have x1 minus x2 or whatever. Okay, so we know the integration ranges. We need to know the differential volume element, which is going to be produced from differential changes in the three variables dr, d theta, and d phi. It's not as simple as just saying dr times d theta, d phi, because if you have a long vector r, a little differential change in the angle is going to describe an arc that's related to the distance r. So you're going to have some extra r's in there, and also a sine theta. So this figure we're going to go back to. The vector r is pointing up in space. The projection of r into the xy plane is going to be r sine theta. Okay? And so in the xy plane, we're going to use a vector of length r sine theta, and then we're going to use the sine and the cosine of that. So x is going to be the length of this vector times the cosine of the phi angle. So r sine phi times the sine theta times the cosine of the phi angle. Now the y is going to be the length of this vector r sine theta times the sine of phi. Now usually you don't have to do these interconversions to x, y, and z, but you do need to understand that there are some transformations you have to take place if you want to convert one to the other. Now z is rather simple in spherical polar coordinates, and that's important because it turns out the math is simpler for the z coordinate than for the x and the y, because for the z coordinate, it's just the length of the vector r times cosine theta. Okay, and so as a result, some operators in terms of the coordinate z is going to be rather simpler in terms of r, theta, and phi. So as a result, let's go ahead and look at the arc of this r sine theta vector. If we change the d phi angle, it's going to be r sine theta, the length of the vector, times d phi, the change in the angle. Whereas if we change theta, the vector that is describing the arc is r, not r sine theta, so that'll be just r d theta. And then if we lengthen the vector by a differential element dr, the change in that little volume element is going to be dr. So we just multiply all four of these together to get the differential volume element. So it's not a tiny little cube like it would be in Cartesian coordinates. It's like a tiny slice of a sphere. So dv, so you got to know this. So if you're going to set up a problem when you're using a wave function and you see r, instantly think spherical polar coordinates, or maybe just polar coordinates, depends on the symmetry of the system. But you instantly need to realize there's three variables, even if you don't see all three. And so when we look at the wave function for a hydrogen atom, the 1s orbital is a sphere, which means it doesn't change with the angle theta and phi. So when you look at the function, you won't see a theta and phi, but there is an angle theta and phi that you have to integrate over. Right, and the differential volume element is r, which appears twice. So you get r squared, you get a sine theta, and then get the differential dr d theta d phi. Okay, and so in general, when we go to spherical polar coordinates, our wave function is going to be a function of r theta and phi. And the whole reason we go to this set of coordinates is that there is a function of r only times a function of theta only times a function of phi only. Okay, and we're going to use a technique called separation of variables, basically, because the variables separate into a function of r without any cross terms of theta and phi, and multiplied by a theta function multiplied by a phi function.